Okay.
That's fine.
All right. So in that case, let's get started. So I would like to introduce Gaston Nieuviarts from University of, I do not know, Marseille.
I did my PhD in Marseille, and then postdoc in Genoa.
Okay. We'll be talking about the Lorentz symmetry from an almost commutative twisted spectral triple.
Okay. So thanks a lot for the organizers and to Thomas that invite me. And so today I want to present you my personal approach to the signature problem in non-commutative geometry. So I will present the main result of my two last papers, which are under review, and try to give you some hint on this signature problem and on how to deal with Lorentzian or pseudo-Riemannian signature within non-commutative geometry. So the problem, the signature problem is the following. So in non-commutative geometry, there exists a reconstruction theorem, but it works well only for Riemannian spin manifold. And there is no such approach for the pseudo-Riemannian cases. So this is a problem at the mathematical level, and this problem became even more important in the non-commutative approach to the standard model of particle physics, because the manifold part in this approach is associated with positive definite metric, so Riemannian geometry. So it's like if the models, which is really nice because it's a unified gravitation and fundamental interaction within a single geometric picture. It's like if its model do not have time. So it's a very big problem for physicists. And so from this problem, many people propose different approach to the signature problems. And so I want to present you mine today. So schematically, what I will do today, I will present you very fastly spectral triple because Devashi did that. And then two direct generalization of this framework, the so-called twisted spectral triple and the pseudo-Riemannian spectral triple. So pseudo-Riemannian spectral triple, it's the analog of spectral triple, but dealing with pseudo-Riemannian type structure like Cohen spaces or Dirac operator associated with pseudo-Riemannian matrix, and show you how this generalization are only parameterized by an operator K that I will specify, and how we can go from twisted spectral triple to pseudo-Riemannian spectral triple through a map that I will define. So it is one of the result of my first article. And so interestingly, I will show you that there is a link between twisted spectral triple, which are Riemannian-like, and pseudo-Riemannian spectral triple, which are pseudo-Riemannian-like, through the K-map. And I will show you that at the level of the metric, this corresponds to a signature change. And after that, I will present you one interesting result I obtained, starting from an almost commutative twisted spectral triple. So the almost commutative structure is the base structure for the non-commutative approach to the standard model of particle physics. And I will show you how considering such twisted spectral triple that I will construct within this structure leads to the singularization of a pseudo-Riemannian spectral triple structure within this framework. So I will make it more concrete, and I will explain what may it mean for the signature problem. So it will come at the very end of my talk. So let's start with a spectral triple. So spectral triple, I will not give all details, but these are the data of an involutive unital algebra with a Hilbert space and a Dirac operator. And there are some properties that have to be satisfied, like compact resolvent. And the main one on which we will focus is the fact that the commutator with the Dirac operator must be bounded. So this is the way we build derivation in this spectral triple framework using the commutator with the Dirac operator. And so something important to retain is that important class of spectral triple are provided by the so-called real even spectral triple.
Sorry, Gaston,
yes.
just maybe so, because there are people in the audience who are seeing it for the first time, maybe just to point out, to be pedantic, it's the operator D is only densely defined. I know you know that, but
sorry?
It's densely defined. It doesn't act on all the page.
Yes, densely defined on H, yes. Yeah, important point, thank you. Okay. And so important class of spectral triple that we will consider are the so-called even real spectral triple. So you just have two other operators, and the algebraic constraints satisfied by the operator between them are specified by this free number that can take the plus or minus one values. And these three numbers are very important because they are related, they define actually the tau dimension of this spectral triple. So these are very important structural properties. And as Devashi says, other important properties are the commuter properties and the first order conditions, and they have to be satisfied. So I stop here with spectral triple, sorry, because it's not very self-content. There will be a lot of materials. And I go to twisted spectral triple. So the short story for twisted spectral triple is that in the context of von Neumann algebra, spectral triple techniques were okay to study type 1 and type 2 von Neumann algebra. It was possible to deal with such von Neumann algebra with spectral triple. But when considering type 3 von Neumann algebras, which are important in physics, for example, because they appear in quantum field theory, there were problems, and it was related to the absence of trace in this context. So I'm not expert in this. You can take a look at the article of Kohn and Moscovici to have more information on this. And so this leads Alan Kohn and Henri Moscovici to the introduction of the so-called twisted spectral triple. So this is the birth of twisted spectral triple to deal with type 3 von Neumann algebra start. And so the novelty in this approach is to add an automorphism that we will call the twist, which compensates for the absence of trace in the type 3 framework. Okay. So after that, twisted spectral triple were developed and studied mainly by Devastato, Transport, Filacci, Landi, Lisi, and Martinetti, Ponge, and also Devashi, I think. So let's go to the main definitions. So the main elements that is that appear in this approach is the so-called twist. So let's define the important properties that the twist have to satisfy. So considering the star algebra, a regular automorphisms, so the twist have to be regular, is an automorphism of the algebra which satisfies the following constraints. So the origin of this constraint comes from the article of Kohn and Moscovici. And this is the only constraint we put on the twist. And the twisted spectral triple is basically equivalent to a spectral triple. You add the twist inside, and the main difference is that you consider the twisted commutator instead of the usual commutator, which is defined here, and require only this one to be bounded. This is the novelty. And this new kind of derivation, because defined derivation will propagate within all relevant structure. I will show you how. So the axiom of a twisted spectral triple are the same as for usual spectral triple, to the exception of the introduction of a new characteristic number, just that can take the following value, that encapsulate a relation with the real structure, and the replacement of the first order condition by a twisted version of the first order. So everywhere you have commutator, here you have twisted commutator. So there are many reasons to do that. And you can find the first introduction of this in the 2 articles of Giovanni Rendi and Pierre Martinetti. So to continue, as we said just before, what comes with this is the so-called twisted derivations. This twisted derivation satisfied a twisted version of the Leibniz rules. And together with that, one form, in the context of spectral triple, became twisted one form. So you just have new commutator here. And the set of one form is now a A-bi-module, but for this product. So instead of having usual operator multiplication on the left and on the right, in this case, you have the twist that acts here. So the connection between left and right action is different in this context. This is something new. And so this new product make the following twisted derivation be a derivation for this product, as you can see here. So this is actually usual Leibniz rule, but with a modified product. So this is a way to escape the problem of twisted Leibniz rules. And it was first given in the article of Conan-Moscovici. It was for the question that you asked just before. And so again, for fluctuation of the Dirac operator that are generated by unitary action, now we have twisted fluctuation, and just to replace usual one form by twisted one form. So many things are equivalent, but the twisted structure on the commutator propagates within the structures. So nothing very dramatic. It's a minimal generalization of spectral triple. And okay, so now some very important novelty in this context is the definition of the so-called twisted product, which is abstractly defined by the following relations. So the only novelty is that the adjoint is associated with the twisted action. Okay, and I will show you concrete example of this product in few slides. And in this approach, we require the twist to satisfy a stronger requirement than the regularity property on the algebra. We ask it to be BH regular. So regular, meaning it satisfies the following relation, but on all of BH. And the direct consequence of this property that comes from this very relation is that the left and right adjoint of this product are equal. So this is a direct rephrasing of the regularity condition. So that you see that there is kind of a connection between the adjoint property of this product and the regularity property. And since they are equal, we can use a single notation for the twisted adjoint given by the following. Okay. with a plus. This is the important thing. And together with a new notion of unitary, new notion of adjoint, you have of inner product, you have a new notion of unitary operator given by the following and the corresponding set. And what is interesting in introducing such structure is that this very twisted unitary operator generate the twisted fluctuation of the Dirac operator. Usually, for usual spectral triple, the derivation, the fluctuation are generated by adjoint action of usual unitary. Here, it's through twisted unitary. And after that, I will give you a concrete example also of these twisted unitary operators in physics. Okay. So now let's go to more concrete case, and we will restrict to this case, the case when rho is an automorphism of B of H. In this case, there is an operator K, which is unitary, that implements the twist, okay? And you can directly express the row product in terms of K by the following relation, where here it's the usual inner product, which is positive, infinite, etc. So in this way, you see something that Devashi presented just before, which is the so-called crane product. It's equivalent to the, it's not equivalent now, but it will become. And okay, so K is not the importance parameter, okay? And so we design the twisted product with K here, the adjoint with K here, and K unitary operator with K. So new notation in this context. It's important to do this like that. And K is first because different K can give the same twist, but conversely, it's not true. So K is the good, how to say, the good notation is with K. So taking a rho to be a star automorphism, the adjoint became an involution. And directly you have the following proposition that say that the very BH regularity condition imply the following strong relation between K and its adjoint. So you just have a phase shift between the two. And so it's very strong. And then the K product is Hermitian and indefinite. So in interesting case of product must be Hermitian only if the phase shift is zero. Okay, and in this very case, you will cover the so-called crane product that appear in pseudo-Riemannian spectral triple structures, and I will introduce this later. So we will only deal with such cases, taking K to be self-adjoint, and we will use the specific notation for the twisted spectral triple with K here on the same level as the other operators. So now we will take a look at the real structure in this context by building a real structure that relates left and right action on the A bimodule. So for usual spectral triple, the left and right action are connected by the real structure. And now we will want to build a real structure that implements the specific relation between left and right left and right action, sorry. Okay, so we start from the usual spectral triple case with the usual relation between left and right actions given by the operator multiplication. This is associated with the following real structure. It's just notation. And then the direct proposition, the direct result is the following. The twisted action previously presented can be related to the following real structure, which is simply the product of the usual real structure, time the operator K. So this is a concrete form for J. We will see that this have connection with the real structure. We can define the pseudo-Riemannian spectral triple context, and also that this real structure are compatible with the K unitary operator since they implement the adjoint action. So the adjoint action on element in the Hilbert space through K unitary operator is given by the following, which rephrased simply by that. And you can show that this rewrite in the following. So you see that J and K unitary operator are connected. And just to make the connection with usual spectral triple, we can find back a usual spectral triple in this special case where K is equal to identity. In this case, the twisted product is just commutator, is just the usual commutator. The current product is just usual inner product. The K unitary operator are usual unitaries for this product. We recover usual real structure and usual adjoint action as we use to deal with. Okay. So the message is that twisted spectral triple, restricted to this case, generalized spectral triple with K as the only parameter of this generalization. And I will present you another extension of spectral triple context and show you how we can conclude on the same conclusion that K is the only parameter of this generalization, something important in this approach. So, okay, let's go to the pseudo-Riemannian spectral triple case. So, an important first point for which there is a consensus in the community concerning the pseudo-Riemannian approach within non-commutative geometry is that the natural space to deal with are not usual Hilbert spaces, but the so-called crane spaces. So let's introduce what are crane spaces first. Given a positive definite Hermitian inner product, so usual one, from a vector space E, together with a self-adjoint unitary operator, K is equal to K dagger, as previously, a crane spaces is defined to be the following pair, provided by the vector spaces and the crane product. So the crane product is not a positive definite inner product, it's an indefinite inner product, a specific class of products. Okay? And so these are not Hilbert space at all, but these are called crane spaces. And these crane spaces are taken, are the good spaces to consider in the pseudo-Riemannian approaches. And I give you directly the definition of pseudo-Riemannian spectral triple. So the definition is almost the same as for usual spectral triple, but you replace the Hilbert space by a crane space, and you consider Dirac operators that are self-adjoint for the associated product, the product adjoint, sorry, the adjoint which is associated with the crane spaces. And samely as before, you ask the commutator with the Dirac operator to be bounded, and etc. So this kind.
Sorry to interrupt again, but can you remind me, I'm after forgetting, what the inner product sub K means?
The inner product?
So with the subscript K. Subscript with
yes,
the
yes.
Please.
Okay. No problem. Okay, where is it? here. Sorry, it was very fast. So the subscript k means that you put k inside the usual inner product.
Yeah.
This is
Good,
the
thank
way
you.
I yes, just not to put k everywhere and how to say being trouble in differentiate it from what we put here. So the k product is provided by the usual inner product with k inside. And a concrete example of such k product is given by quantum field theory in Lorentzian quantum field theory, sorry, where k is provided by the first gamma matrices, the temporal gamma matrices. Maybe for physicists, it's something known. And so it's something that appears in quantum field theory. Yes. So the interest to consider such pseudo-Riemann spectral triples is that they undo the Lorentzian case, which is of interest in physics. And again, we retrieve standard spectral triple from the definition. In this special case, k is equal to identity. Why? Because this will be the usual inner product, because k is identity inside. And then the adjoint will be the usual one, and the Dirac, which is self-adjoint, will be self-adjoint for the usual adjoint, etc. So you recover usual spectral triple in this case. So it's just another generalization of spectral triple, only parameterized by the operator k. So now, after giving you this abstract definition, I can consider a more concrete example to go smoothly to the manifold case. And it will allow me to introduce the twist within such structure and to show you some interesting results I obtained. So I will only deal with even dimensional vector spaces because I obtained the result in these cases, and I have to extend this result now. And because they undo the Lorentzian case of interest in physics. So let's start. So starting with an even dimensional real vector spaces with metric G with the following signature. We can define its Clifford representations, which are complex linear representations. So V is real, but we use a complex linear representation with the following relation to the metric, so classical Clifford relation. So the elements C of B are complex square matrices, simply. And the complex Clifford algebra is generated by such elements and the identity elements. And interestingly, in the even dimensional case of interest, everything is simple. The algebra is simple, the Clifford algebra is simple, meaning that any automorphisms of the Clifford algebra are inner, something that will be important for the coming results. And okay, and so to undo all of that with a Hilbert space structure, we can consider an irreducible representation for the Clifford algebra provided by the following module, together with this inner product, making allowing to build this Hilbert space with the following options. And now come some important definition. The definition of the so-called cultural operator. So the only novelty concerns the twist here, because the grading and the charge conjugation operator also are already well-known operator are defined in the Clifford algebraic context. So the structural operator called twist, grading, and charge conjugation are defined to be automorphisms of the Clifford algebra, such that we have for any vectors the following relation that holds. So for the twist, the action of the twist on the Clifford algebra give the adjoint of these elements. And these are automorphisms and not anti-automorphisms, because this adjoint, the transformation to the adjoint is only valid on the Clifford algebra. So it's a property only on the, decorated vector space. Something important to notice because there are some confusion most of the time. So this is the definition of the twist within this context. And a direct consequence is that such a twist defined like that is BH regular. Okay, so very nice property for as before, and important for build the connection with twisted spectral circle. So let's continue. As any automorphisms are inner, there are operators that implement the structural operators. So you recover K, the grading within spectral triples, and the charge conjugation operator, something known in physics that allow to build the real structure in optics. And if now we require, we propose this following G orthonormal basis for V with unitary elements for the representation. Then, interestingly, the plus and minus eigenspaces induced by the twist and the metric coincide. Okay, and this directly rephrase like that. So it's make the twist be the parity operator itself. So parity operator is an important operator in quantum field theory. So the twist, the interpretation for the twist is that it is the parity operator. And again, for positive definite metric, we have the following, meaning that this corresponds to the case K is equal to identity. Okay, so now some important results that connect the twist to the orthochronous spin groups is the following. So the orthochronous spin group is a subgroup of the spin group, which corresponds to the subset of elements in the spin group that preserve the orientation of V plus minus, where V plus corresponds to the vector space, the subvector space, which corresponds to plus metric, and minus to the minus metric. So this means that the orthochronous spin groups preserve the spatial and temporal orientation independently. And this very group is of interest in physics because it's the direct generalization of the Lorentz group, which is the good group to consider for the symmetries in physics. So the result is that taking any element in the orthochronous spin group, we have the following relation between these elements and the twist. And this directly means that the natural invariant inner product for this group is provided by the previously given K product. Okay? And this means that thanks to the fact that rho is BH regular, you can rewrite this in the following, making any element in the orthochronous spin group be a K unitary operator. So here you see that the K unitary operator that I defined in the twisted spectral triple context now have a particular realization with the orthochronous spin group, which is the direct generalization of the Lorentz group. Okay, so let's go. Now, in the same way as for twisted spectral triple, let's take a look at the real structure in this context. So the real operator is usually defined from the charge conjugation operator previously defined and the complex conjugation operator. And if we build the following vector space at the level of the Clifford representation from V by a weak rotation, which means that you multiply by complex number E any temporal element in the basis. Then V8 is associated with a positive definite metric naturally. And you can associate this new vector field with the following charge conjugation and real operator. So same as before, you recover the notation. And the proposition is the following. We have a relation between K for V, K8 for V8, and the twist given by the following. And this directly implies that the real structure here is connected to the real structure of positive definite metric by the operator K. So we recover exactly the same kind of real structure as in the twisted spectral triple context. So it's another connection between twisted spectral triple and pseudo-remanent spectral triple. And it's important element for what. So we will require K and the grading to be self-adjoint naturally, and this will directly imply a simple relation between K, J, and gamma provided by the two numbers epsilon and epsilon prime. In the same way as the epsilon 0, 1, and 2 for the connection between D, J, and gamma. So let's go to the manifold case. So everything I said before will become a local in the manifold case. So let's consider a smooth even dimensional manifold with previous metric. To any element V in the local tangent spaces, we can associate as before its Clifford representation and then build the Clifford bundle like that. The inner product will be locally defined and the corresponding train product also. And using G orthonormal basis of the cotangent space, you will define the so-called gamma matrices, which are very famous in physics. And from these gamma matrices, the full Dirac operator with here the Levi-Civita spin connection. It's a usual construction. And from that, you can define the pseudo-remanent spectral triple corresponding to the to this manifold by the following, taking the algebra of smooth function on the manifold, which is commutative, the crane spaces, and the Dirac operator, which is self-adjoint for the corresponding adjoint. Okay, so now I can go to an important step, the relation between twisted and pseudo-remanent spectral triple. So I present you some connection, but now I will make it more concrete and build this connection in the end. So what I propose you is to define the so-called K-map here, which is a map that connects twisted spectral triple and pseudo-remanent spectral triple. So the K-map is a bijective involutive map only parameterized by K, which permits the transition from twisted spectral triple to pseudo-remanent spectral triple. So it's bijective, so the arrow is in the left also. And this is defined by the following actions on the Dirac operator provided by this, and on the derivation and the Hilbert space structure. So basically, you see that you can connect self-adjoint operator for twisted spectral triple with train self-adjoint Dirac operator for the pseudo-remanent spectral triple by these very simple relations, and you can check that this holds. And you can conduct twisted derivation from this, and usual derivation in this pseudo-remanent spectral triple context with the same relation and connect also the product very simply. So you can directly notice that this relation preserves the boundedness of commutator, so the important properties in the definition. And other important properties concern the self-adjointness properties of the Dirac operator, which is concerned. And also, the first order condition are related by K also, meaning that if one first order condition is satisfied, then the other is also. So that at the end, the K-map give a one-to-one correspondence between twisted spectral triple and pseudo-Riemann spectral triple. Okay, and all this relation that work also for the derivation extend to the level of fluctuations. So there is a compatibility with all these structures. So this is the full connection between the two contexts. You can see that the K-map do not act on the Dirac structure, which is not a problem, because I show you that the Dirac structure are connected in the two contexts, and that in the twisted spectral triple context, they are related with the twisted product one by module. And okay. So now I want to show you what does it mean in the context of the manifold. So what does it mean? Mainly at the level of the matrix. So if we start from the previously defined pseudo-Riemann spectral triple associated with the metric G, we can define reflections on this manifold as isometric, so J isometric automorphisms on the tangent space, which are involutory. Okay, so this is the definition of reflections. And particular kind of reflection, or the so-called space-like reflection, which are reflections that permit to define positive definite metrics by the following action of the reflection within the metric. This is the definition for space-like reflection. And very simply, this means that when space-like reflection act on temporal components, it do not change their orientation, but when it acts on spatial component, it changes the orientation. Okay, so there is a minus sign. And from that, directly, you train a geometric interpretation for the twist given by the following. So the twist previously defined in the context of Clifford algebra actually implements a space-like reflection at the Clifford representation level. So the twist is equivalent to a reflection on the vector spaces that is represented. So this is a simple geometric interpretation for the twist here. And it will be interesting in what follows. And just a remark, you can rewrite the previous relation here at the Clifford representation level by the following, where the twist here, which can be replaced here by the following, okay, which is that just a rephrasing of the Clifford representation with this metric. So now the question is concern the metrics. So now, starting from the pseudo-Riemann spectral triple, we construct the associated twisted spectral triple with the K-map, and we ask what is the corresponding metric in cone distance formula for this twisted spectral triple. And the direct answer is that the associated metric is GR. This is the previously defined positive definite metric. And when you do the computation of the distance formula, you see explicitly this that appear within the computation. and which lead to the positive definite metric. So this means that the K-map acts on the metric as a local signature change. So this is something new. This is local because K is locally defined. And you can take a look if you want at my article for more results on the action of the K-map on the Clifford structure and also the Christoffel symbols, because here the result is only at the level of the metric. And I think what is interesting is provide an alternative to weak rotation to do the signature change process. And this alternative do not involve any complex numbers. So there is not all of this problem with the fact to complexify some coordinates and the approach. There is nothing like that. It's the only reflection operator, space-like reflection, that do the job. Okay. So I can stop with that and present you my last result, which concern almost commutative structures. So the very structure at the heart of the non-commutative standard model of particle physics. And the idea was to build almost commutative structure on this kind of twisted spectral triple to see what happens. So there were many motivations to do that, but I will just motivate this by the result that I will present here. So now the point is to construct an almost commutative spectral triple on the twisted spectral triple. We ask this twisted spectral triple to have algebraic constraints that correspond to a chaos dimension 6 pseudo-Riemann spectral triple. It's a choice motivated by physics because the Lorentzian case corresponds to chaos dimension 6. And so we start in this top-down approach with the following twisted spectral triple that satisfy the following constraints. And we associate this within the almost commutative structure with a finite dimensional algebra, also in chaos dimension 6. So the motivation for that can be found in an article of John Barrett. And so actually the chaos dimension 6, chaos dimension of the finite part in the non-commutative standard model is 6, because there are many arguments, connection with Fermi-Doubling problem and other important things for physics. So this defines a top-down approach. So the full spectral triple is given by the following. You have the product of the algebra of smooth function on the manifold and the finite algebra. The following Hilbert space, that structure. The twist is the combination of the trivial twist and the usual twist, so natural extension here. And for the Dirac operator, you have the following with a generic operator for the moment that will be specified. And so the algebraic constraint for the full spectral triple are given by the following. And this very constraint leads to constraints on the operator O, which are given by the following. And these very constraints are exactly the constraints the operator K must satisfy. So from now, we will put K in the place of O because these are exactly the same algebraic constraint. And one other motivation to doing so is that this choice ensures the existence of independent derivation in the full derivation on the total spectral triple, which means that if you do not take care here, you will not have a derivation for the manifold part and derivation for the finite part here, but something totally mixed. So you lose everything which was interesting in the usual approach to particle physics. So another point is that this gives kind of relation between twisted structure and the presence of K, which originates from the almost commutative structure here, making, in a way, a twisted spectral triple be considered as a subpart of almost commutative structure. So it's just an idea, a point of view that I share with you, actually. And we can continue. So from the fact that we write the full Dirac operator like that from now, you can directly rewrite the full Dirac operator by factorizing it with K like that. And you see that the pseudo-Riemannian Dirac operator emerge here. And some important feature of K is that it is associated with the finite part, meaning that it's fixed for the symmetries of the manifold part. The symmetries can be the groups that act on D, for example. And this equality extends to the fluctuation of the full Dirac operator by the corresponding unitary operator, a tensor identity unitary operator provided by the following. It's just extension of what I presented previously. So it's natural. And let's go to another point. So you see that the pseudo-Riemannian Dirac operator appear here naturally. And in the non-commutative approach, the way to extract the Dirac action, which is the important action in physics, in quantum field theory, is by computing the evaluation of the full Dirac operator by the full inner product. So let's define the inner product now. The inner product on the almost commutative spectral triple structure is provided by the product of the two inner products, the one for the manifold, the one from the finite part. So it's a usual way to combine products over tensor product, inner product, sorry. And you can associate this product with the corresponding train product like that. And the direct result is that when you compute the fermionic action, the way to obtain Dirac action in the approach, then what you obtain is that it rewrites in the following, with K product appearing here and here. And for physicists, this is exactly the good shape we need for a good Dirac Lagrangian, because you have a pseudo-Riemannian Dirac operator evaluated by a train product. These are the gamma zero matrices that are put in the adjoint field, and the mass term together with the K, which is the first gamma matrices here. So this is exactly the good shape we need to obtain the Dirac Lagrangian, which is Lorentz invariance. And this rely on the fact that K is a fixed structure, meaning that you can put it outside and it is untouched by the symmetries of on the manifold part structures. So interestingly, the very fact that K is fixed singularized within the full structure a pseudo-Riemannian spectral triple, putting the Crane structure and its Dirac operator to the foreground. Okay. And the essential thing is that it's their symmetries that is important here. It became the important operator to consider. And Okay, so let's consider what does it mean for the implicit pseudo-Riemannian metric and Dirac operators. So the thing is that from D you can construct the pseudo-Riemannian Dirac operator, which will be associated with the corresponding gamma matrices parameterized by the choice of K. The corresponding metric is also parameterized by K. Everything depends on K. And at the end, the signature of the metric Jk is determined by the choice of K, which itself is determined by the algebraic constraint coming from the full almost commutative twisted spectral triple structure. So these are the following relations. And we now ask if these conditions are enough strong to specify clearly the signature of the metric. And we will only do this in the four-dimensional case of interest in physics. So the proposition is the following. In dimension 4, the operator K that satisfies this condition coming from the almost commutative structure induce the transformation from a positive definite metric for the twisted spectral triple to pseudo-Riemannian metric with signature plus minus 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 when you take the following choice for epsilon and conversely for epsilon is equal to 1. So this is interesting. This means that in the four-dimensional case, there is only one time. And when you take epsilon is equal to -1, you recover the long Lorentzian quantum field theory cases directly. So from algebraic constraint coming from an almost commutative spectral triple structure, you recover one dimension for time and the good structure, the good kinetic term in the Dirac Lagrangian from this term in the full Dirac operator, and also the good mass term. Okay, so this suggests that there may be a connection between Yang-Mills model and Lorentzian signature, making time be, in a way, a consequence of the geometrization of fundamental interactions. This is what is done in the non-commutative standard model, particle physics, that is like an extended gravitation theory in which all interactions are geometrized. And this makes time, in a way, be a consequence of the non-commutative part that we add in this structure to geometrize the fundamental interaction. So this is my point. And thank you for your attention.
Thank you, Gaston. Are there any questions from the audience?
Maybe, but if you go back to the definition you had, sorry, this was the pseudo-Riemannian spectral triple, where you had the question that I was asking before about this inner product that was going to be sort of twisted by the matrix K.
Yeah.
This guy. I'm just wondering then, on this, what does self-adjoint mean?
Okay.
In a sense, like, so if I have a huge, just to recap, so people I'm talking
Yes,
about,
yes, important point.
If I have a usual spectral triple, the self-adjoint, I mean, I'm defining the domain of the adjoint in terms of the Riesz representation theorem, and I ask that the things match up and blah, blah, blah. Does this all make sense when you've twisted the inner product in the way you have?
So you ask what is the meaning of this new adjoint?
Is the twist of the self-adjoint unbounded operator, does it twist easily, or is there subtleties, or?
So sorry, I have problem to hear you with the micro. Yes.
Sure. Space. Self-adjointance is subtle. You have to go through steps. You construct the domain of the adjoint, and then you construct the operator on this, and then you have to show that the domain of the operator and the domain of the adjoint are the same, and then the two operators coincide. And that relies upon the Riesz representation theorem. Does that construction just get twisted in some sense?
Does this construction relate to twist?
Yes, yes.
To twist. So the only relation with the twist here come from K, and K permit to define the inner product, the crane product here, from the usual inner product, usual inner product for Hilbert space, and K put here. And from this new product, you can define a new notion of adjoint, which is basically provided by the following action. Okay? And in the pseudo-Riemannian spectral triple from Rohr, you consider this crane product, the associated adjoint, the K adjoint, and you require the Dirac operator to be self-adjoint for this adjoint. And the only relation with the twist come from K, which is essential to define the product, then the associated adjoint, and then the constraint on the K. I don't know if I answer.
I'm not sure. Let me ask another question. So do you have an usual unbounded operator, densely defined unbounded operator that's a self-adjoint. You'll have an associated unbounded functional calculus. I use allowing you, for example, to define the bounded transform and relate your spectral triple to K theory. Is there an unbounded functional calculus for this dagger K self-adjointness condition? Sorry, it's a very mathematical question.
It's a good question. I do not have the answer, but this definition come from an article by Stromae. If you want, I can put this in the chat, where he defined very mathematically a pseudo-Riemannian spectral triple, and I think he answered to such question, but I'm unfortunately unable to answer right now. So
that's okay.
So I can put this in the chat at the end. It's a very important article. For me, it's one of the main articles in the topic. And you can find this definition, and you check many important things. But I don't know how to answer.
Okay, thank you. And is there any, at the final question, of the pseudo-Riemannian, a more general question, is there at this level some sort of a reconstruction theorem in the sense of Kahn?
Yes, the main, the signature problem is the following. You do not have reconstruction theorem in the pseudo-Riemannian case. So everything that works well with Riemannian geometry, spin Riemannian geometry, go with usual inner product structure, usual Dirac operator, which are self-adjoint, etc. And these very properties are essential in the process of reconstruction, the reconstruction theorem proof. And so in the pseudo-Riemannian case, we do not have such theorem, and it's a big problem. And in a way, it's like if pseudo-Riemannian geometry is not natural within the context of spectral triple, because the strength of spectral triple come from the reconstruction theorem, because it's a way to rephrase Riemannian spin geometry in a purely operator theoretic language. So this is all the problem with the pseudo-remanent spectral triple approach is that there are no reconstruction theorem. And many people have different point of view on this problem, and it's a big problem in the community. Actually, there are many attempts to solve this problem. And my point was to say, okay, pseudo-remanent spectral triple may not be fundamental, not object to take at first because they are not natural in this framework, but maybe emergent things, and my proposition go with this value.
Okay, thank you. And here, I'll have one very last question then. So you spoke earlier on about the associated differential calculus, the generalized differential one forms. Does that work in this case as well, in the twisted? I mean, you have your bounded operator, so there's an obvious guess, but
so your
this
question?
This is at the twisted level, but at the level of the K, the pseudo-Riemannian level, does this work?
Yes. For pseudo-Riemannian spectral triple, things are basically equivalent as for spectral triples. So you can construct one forms in this context, and similar structure as for spectral triples. And I think there are no problem to do that. And at the end, I did the computation. You can have fluctuated Dirac operator in the same way through this relation with the Lorentz structure, etc. And I did not find obstruction to do exactly as we do in the spectral triple case.
Okay. Thank you. Thank you.
Thanks a lot for your questions.
Okay. Any other questions from the audience or from the online participants? No? If not, then let's thank the speaker again. And we'll see each other again next week. Thank you.
Okay. If you want, I can put the link of the article just in the chat.
Yes.
I stop the sharing.